So I would say this chapter 6 material is usually some of the more challenging material. There's just a lot of, this could have easily been 2 chapters, but for some reason it's all rolled into one because it all has to do with energy, but we will spend a little bit longer than a normal chapter on this. So we're still at the very beginning kind of ideas. And I think I broke it up into 3 different reading sections rather than 2 for the chapter, just because there's so much stuff in here. But it's about different kinds of energy concepts, and the one we've been talking about so far is work, which we just gave as a definition. And we're practicing following that definition. And we gave a more general case where we didn't align the displacement with a particular axis, but the version that you'll see in Giancoli, I believe this formula that should appear in Giancoli, that's where you say some object is moving from an initial to a final position. Maybe it's moving the whole time. Maybe it was moving before the initial and after the final, but we're just going to define an initial and final. And we're going to align one of our axes between the initial and final states so that its displacement is only along, say, the x direction. And then in that simplified case, the work done by a constant force that's applied through the displacement, and it could be undergoing some complicated path. Here I'm showing it going along some arc. The force, if we're going to use this formula, the force has to be constant. We'll talk about what to do in cases where it's not constant, because not all forces are constant, but there'll be something like gravity, right? Gravity's, if something's moving around in space between some space, gravity is always constant in magnitude and direction. It's just the weight of that object. Okay, so Fx delta x. And we practiced using that a little bit Monday. And one of the things we observed right before the end of class was about the sign of the work done by a force. If a force, as an object is moving, maybe 4 different forces are acting on it as it moves from initial to final. We could calculate a work associated with each force. That's why we put that complicated subscript on it. The work done by this force on this object. It's going to really help to be explicit about that when we have lots of forces. So thinking about a particular force, if it's pulling or pushing more or less along the direction the object is moving, that corresponds to a positive work. It just comes out of the definition. If the object is moving in this direction and I'm applying a force, I'm trying to hold it back, right? But it's still moving in the opposite direction from which I'm applying the force. That's the hallmark of negative work. Even if I'm just partially pulling back in that direction with the string as it moves in this direction, that would be negative work. And 0 work corresponds to when a force, that force does 0 work when it pushes or pulls perpendicular to the direction of the displacement between initial and final. So we were practicing with that at the end. And I guess I have some examples up here. And I think I sort of said this kind of stuff. If I'm lifting a book with my hand underneath, the forces for the free body diagram roughly are there. And let's suppose I'm lifting it up. My hand is pushing up on the bottom of the book. Gravity's pulling down on the book. So there are 2 forces acting on the book. Gravity's doing negative work as it's raised up. My hand's doing positive work because I'm pushing more or less along the direction of displacement. Gravity's pulling downward, opposite direction of displacement. When I lower it, gravity's doing positive work and I'm doing negative work. When I carry it horizontally, both forces are doing 0 work because the displacement is horizontal and both those forces are only in the vertical direction. And if I hold it motionless, seems like a ridiculously simple thing, but just to emphasize the fact that we're using a word that we use in everyday English, I might, if I'm holding a barbell here, I might say, I'm doing a lot of work holding this up. But we would say in the physics sense, you're doing 0 work. Even though it takes a lot of effort to hold that barbell up, there's got to be a displacement over which the force is acting for there to be work. So don't mistake it for effort, even though doing work does take effort in the physics sense, but you can do effort and not do any work. Now, so here's a new definition or a new way of using words. the network. And you got to kind of hold your breath at the beginning of this chapter, because we're going to find out why we care about work. Right now, it's just a definition that I made up or Giancarlo made up, but we'll see why it's useful. And the network is part of that. So network just means like net force. You add up all the works done by all the forces that are acting on an object as it moves from initial to final. Okay, so we have to consider all the forces and add up all the works. Some of them may be positive, some negative, some zero, but we just add up all those works. So if I imagine an object undergoing a displacement delta x and I align my x-axis with the displacement direction, then I have to add up all these works, right? I've got a force F1, I take its x component, another force F2, take its x component, and so on. Add them all up for n different forces, and I get the same displacement. If we're talking about just a rigid object, we have the same displacement appearing in every one of these terms, so I could factor it out there. And when I factor it out, what's left in the parentheses, notice, is the x component of the net work. So another way of thinking of, of the net force, not the net work. This is the x component of the net force. The net force just means add up all the forces, and we're adding up all the x components of all the forces. So another way to think of the net work is, rather than adding up all the individual works, you could say, well, let's just compute the x component of the net force and see how much work it does. In other words, think of the net force as just a single force, even though many forces may be contributing to it. Sometimes we'll think of it that way. Okay, a little voting question having to do with net work. Here's a heavy box, rough surface right here, so there's friction. And we're going to pull with a constant force along some angle, more or less along the direction from A to B. And all we're told is that, as time goes on, the box first passes A and then later passes B, and we want to find the net work done on the box in going from A to B. That's our initial and final. What do we know about the sign of it? Is it positive, negative, or zero? Impossible to determine, and there's two different ways that it's said to be impossible to be determined at the bottom. You got to kind of think of several forces here, right? I've shown one force, but there are more than one force acting here. If you don't have your voting card, just use 1, 2, 3, 4, 5 with the hands like that. Okay, let's see a vote now and see if there's a consensus, or at least something close to a majority. I'm seeing a lot of A's and B's. Positive. Anybody want to argue for positive or zero? Probably saw 2/3 of the class holding up one of those two. More A's than B's. Yeah, certainly it is. We're told that it first passes A and it later passes B. That's going to be our initial and final. So it is getting displaced to the right. Maybe if we thought about the forces that are acting, what do you say, Arthur? Well, we don't really. Of course, we could choose any axes we want, and it might be simpler when one set of axes to compute the work. But the claim is the work we compute won't depend on the axes. And that's something I should have emphasized earlier, that it's actually independent of your axis choice. So do whatever's simplest. And in this case, it's probably simplest since it's sliding directly horizontally to the right, even though I'm pulling up with that rope a little bit. To check your x-axis horizontally, and then I can just do Fx delta x for each force. So technically, you don't need to know it. You should get the same answer no matter what axes you choose. Anybody else have a strong opinion about it? Yes.
I have a strong opinion that if the friction force was too great for the work that was here, that means the box is moving.
Yeah, well, it's sort of suggested here that it does get from A to B. So it is moving somehow. First it passes A and then it passes B. Somehow. We're not told a lot of information about it. But Could it be the case that the friction force is really big and I'm putting a really wimpy force on with the rope? What would be happening if that were the case? Suppose it started out moving. Someone gave it a kick. It's moving in this direction, and I'm not pulling hard enough to overcome the friction force. What's going to happen as time goes on and we move from A to B? Yeah, or it would either stop or it might slow down, right? Here, presumably it didn't stop between A and B because we said it passed B. So, but it could slow down, right? So it's like it was initially moving and I'm sort of trying to pull it in this direction, but I'm losing out and it's slowing down as it goes from A to B. Or I could be pulling really hard, right? So maybe I'm pulling with an extreme force and it's actually speeding up as I go from A to B. Or I could do what, a lot of people imagine when they look at this, and that's that I'm just pulling at a constant velocity, that box. Do you have any intuition about those three cases, what that would correspond to with the net work? If we go back to the second way of thinking of the network is we just have to think about the net force x component times delta x. So if it's speeding up here as it goes from A to B, going faster and faster, which way does the net force point in the diagram? Yeah, a lot of people are pointing with their hands to the right because it would be accelerating to the right. And so therefore the Newton's second law says the net force has to point to the right. If it's slowing down, it would be accelerating to the left, right? It's moving to the right, but accelerating to the left. That's one of those confusing cases when we first talked about acceleration. And therefore, the net force would have to be to the left. That's like, oh, big friction force, not quite so big pulling force. And so the friction force is winning out and the net force is in that direction. Or if my force x component balances out exactly the friction force magnitude, then zero net force in that case. So the correct answer here is that it's actually impossible to determine. It could be positive, negative, or zero. Some people, when they read this, they assume it's being pulled at a constant speed. I'm sympathetic with that, somewhat of a trick question that way, but it could be speeding up. All we're told is that I'm applying some kind of constant force and it somehow makes it from A to B. So it doesn't stop along the way. Okay, so it just depends. The point here is that you've got to think about a lot of forces. There's a normal force. How much force is the normal force doing as it moves from A to B? Zero work, right? Because it's perpendicular. That's the hallmark of zero work done by a force if it's perpendicular to the direction of motion. Yes?
I don't understand if delta x is part of the like it said the passage by.
Yeah, so we said one way to must have picked up the one that was worn out before. Let's get a real marker here. One way to think of the net work was to get the net force x component and then multiply by delta x. Now, if I'm pulling it at constant speed, which you probably have the intuition that I could do that, right? If I adjust my tension just right, I could drag it at constant speed to the right. What do you think about the net force? Well, even before we take the x component, what would the net force be in that case? If I'm pulling it at constant velocity to the right, it's zero because the acceleration is zero. Anything moving at constant velocity has zero acceleration. So therefore, the x component has to be zero in that case if I'm pulling it at constant speed. So it doesn't matter that this is non-zero, it's being multiplied by zero in that case. I could make this be positive. I could also make it be negative by pulling harder than friction or letting friction win and it's slowing down as it comes over there. Yeah. All right, good. Let's do some more examples with me holding things here and moving them around. So lifting a book, well, maybe it's best to point at the slide here, but I'm imagining I'm lifting a book at constant velocity. So in going from this bottom position, I'm going up at a constant rate and it's passing the initial and then the final position. In that case, the only relevant forces are my hand force upward on the bottom of the book and gravity pulling down. And they've got to be balanced because it's moving at constant velocity, zero acceleration. and therefore they're balanced. And the hand force would do positive work. The gravitational force would do an equal and opposite amount of negative work. And so the net work would be 0 there, right? In this case, if I'm moving at a constant velocity. Let's suppose instead, oops, wrong way. Yeah.
The force of the force is going up, would that be the force you're applying and the normal force?
Well, my hand is kind of like the normal force in this case, right? This thing is sitting on a surface, which is my hand. So, I could have put it on a table and lifted the table up, but it's sitting on my hand. So you could call it a normal force. I just happen to call it a hand force here, but same thing. Now, if I accelerate it upwards, in other words, going faster and faster vertically as it rises, to do that, it's got to accelerate up. And that means my hand force has to be bigger than the gravitational force in magnitude. So there's a net force upward. And that means my hand is going to be doing more positive work than gravity is doing negative work. And so there would be positive net work done on the book in this case. Similarly, if I'm slowing down as it goes up, raising it upward as it's slowing down, then my hand force has to be smaller. So I do less positive work, more negative work done by gravity. So the net work would be negative. And so, you could think of lots of different cases that were like that. Okay, questions before we move on about net work. We'll use that on that same worksheet that we were working on a bit ago after a bit more development here. This is just a side note that I think Giancali talks about this sort of on the side too. There's a way to calculate. So we talked about this formula for calculating work, the Fx delta x only works if your force is constant in magnitude and direction all the way from initial to final. Now, there is a way to calculate work for non-constant forces, and it's related to ideas that some of you may have seen in calculus. And we're just going to talk about a geometric picture here. So we're going to imagine, just for simplicity in this example, an object moving along the x-axis and some force, or maybe we'll just add all the forces together, some net force acts on it as it changes position. So it's just moving along the x-axis. Sometimes while it's moving along the x-axis, there's a force pulling it forward along the direction it's going, and then other times it wants to go back. So maybe it's like an object. Maybe the object is moving along the x-axis and it's like a car. And when the car's got the accelerator being pressed, that means there's a force on it pushing it forward faster and faster. And then when it hits the brakes, that's when the force is in the negative x direction. Okay. In this case, the force might vary continuously. It's certainly not a constant force, but I might say, well, when the force x component is positive, that means it's being pushed along the positive x direction. At this later x position, further out on the x-axis, there's a negative force x component. I'm graphing the force x component as it moves along the x-axis. This is where it's applying the brakes here. This is where the accelerator is on, right? It's pushing in the positive x direction. Now it's slowing down, so it's, the brakes are being applied as it's pushed along the positive x direction. So the force is certainly not constant, but we could just consider a very tiny bit of the motion that's shown in green here, just a tiny step forward as it moves through it from small initial to final position there, and calculate the work that's done. Well, notice if it moves through a small little position delta x, the height of the curve is the force there. And notice that for that small delta x, the force doesn't change too much within that very small region of the x-axis. So the force is approximately constant, and I could treat it as if it's actually constant there. And if I notice the height of the curve is f net x, this is delta x. So I could interpret the area of this rectangle right here as the net work done on that object in this little small displacement. I'm showing that as just the area of that blue rectangle. And then as we move forward in the next delta x, we would use a different average delta, and we would just add all these up and calculate the total area under the curve. So as it moves from this very negative x over there to a very positive x, the idea is if you want to calculate the net work done by a varying net force as it moves along x, you have to calculate the area under the curve. And if you've taken some calculus before, maybe you know that means the integral, which we're not going to be calculating things like that in this class, but sometimes you might be able to do it geometrically. Okay, so I want to talk in general about the kinds of objects that we're going to be calculating work on and calculating energy concepts on, and start with complicated ones. And we're going to whittle it down to the simplest case and work on the simplest case first. And then we're going to step up to a slightly more complicated case, and then we'll get to the most complicated case in the end. So the most complicated kind of object, we've been treating things like boxes. They're not at all like this. This is an object where there are several different moving parts, and there are forces between the moving parts. And so the object, this object consists of, like, 4 masses connected by 3 springs. It doesn't even have to have the same shape as it moves from initial to final. Most complicated object might be like a human body, right? Someone dropping from a building, and your arms are flailing. All these little bits of mass could move, and your muscles are applying forces between different parts of it. Super complicated. So we're going to wait to treat this kind of case. We'll never treat the human body, but we might treat a couple of masses, point masses connected by springs later on. A somewhat simpler system that we might consider how much work is done on it and how the effect is a rigid body, like a book or something like that, that's not changing shape, or a piece of metal. But it still might rotate in between the initial position and the final position. My block here, I might say, oh, it's a rigid body, but it's rotating and tumbling over itself as it moves from initial to final. That's still somewhat complicated, so we're not going to deal with that right away. The case we're going to start with is where we have a rigid object, only one object, and instead of tumbling or rotating at all it does is translate. So that would be like this block. As it moves around, and those of you who are on Zoom, I'm not going to undo the camera here, but if you look at mine, as this moves around, notice it's not rotating. So we would say that this block is behaving like a particle. Its motion is that of a particle. If it starts rotating, it's not particle-like anymore. Certainly, if it's squishy and it starts compressing and then expanding or something like that, that would be very unparticle-like. But particle means rigid body that only translates. It can translate all over the place. It can go up and down, but it can't rotate at all in between initial and final. So we're just going to consider that kind of motion. Our box sliding down the inclined plane, that box is behaving like a particle. A lot of the cases we've been thinking of, if I toss a ball up and it's not rotating, and it goes up and then comes down on that arc, it's behaving like a particle too, if it's not rotating in between some initial point and some final point. So let's narrow the field and just think about that. We're going to start thinking about some particle moving from initial position to a final position. Could be sliding along an inclined plane or something like that. And we're going to use our knowledge of kinematics to relate the work done on it by all the forces, the net work done on it, to something about its change in speed. So let's denote its displacement. We choose an initial and final state. Let's denote its displacement by delta R. And there could be a lot of forces acting on it. For the time being, we're going to take the simple case, and we're going to assume all those forces are constant in between initial and final. Although, if we're willing to interpret areas under the curve, we can kind of relax that later on. So here I'm imagining there are 3 separate forces acting on this box, this particle, as it moves from initial to final, but they're not changing. They're always the same magnitude in the same direction. I'm just showing those by the 3 arrows there. Since the forces are all constant, that means if I just add them up, I would get a single net force that doesn't change. There's one net force, which is the sum of all the forces, which is just isn't changing. Since the net force is non-zero, that means the acceleration of this object is non-zero. And since it's accelerating, one thing to remember is that it's not necessarily just moving along a straight line there. Acceleration means the initial velocity and the final velocity probably don't match. Right? When something's accelerating, the initial velocity and the final velocity, there's a change there. So here I'm showing, it was going down and to the right at the initial state. Because it was accelerating up and to the right, it ended up moving up and to the right later on after it accelerated for a while. So you got to remember that there could be some change there. And in this case, the acceleration is constant because the net force is constant. So we're going to apply constant acceleration kinematics. We know when we use kinematics, we got to keep our x's and y's separate. And so in order to do that, we're going to put some axes on here. So let me take in this just picture to kind of derive this thing. Horizontal is x, vertical is y. We'll break up the net force into x and y components. We'll break up the displacement into x and y components. We'll break up the initial and final velocities into x and y components. And now what do we know about those initial and final velocities? We know that their x and y components have to satisfy that kinematic equation that is the one involving the squares, right? Vx final squared is equal to Vx initial squared plus 2ax times delta x, and the same one for y. Okay, so that's something we are familiar with from before. And we're going to change this pair of equations into something that tells us about work, strangely enough. Here's how we'll do it. Maybe you can imagine. We've got some accelerations in there. That's related to net forces. And net forces are related to net works. So let's try to go down that path. The acceleration x component is the net force x component divided by the mass, right? That's just F net equals ma x component. Same thing for the y there. And now what we're going to do is take these two separate, almost kinematics equations and add them up. We're going to add, if the left side equals the right side for both of these, then the sum of the left sides must be equal to the sum of the right sides. That's all we're doing. And on the left-hand side, I'm going to get Vx final squared plus Vy final squared. And if you think about that for a second, that's usually how we calculate the square of the final velocity, right? The square of the final velocity would be the final x component squared plus the final y component squared. If I took the square root, I would get the final, not velocity, but speed. This is the square of the final speed. This is the square of the initial speed. So when I add these two equations, on the left-hand side, I'm going to get the square of the final speed. On the right-hand side, the first two terms are going to be adding to the sum of the initial, sorry, just the initial speed squared. And then there's a mess left when I add these two things. Notice they're not the same things, right? I've got a delta x and one involves x terms and one involves y terms. But now I look at this and I'm saying, oh, that looks a lot like work in there, right? I've got an F net x times delta x plus F net y times delta y. In this case, there is no guarantee that we aligned our x-axis with the direction of displacement. We definitely didn't here. And so we better use the more general formula for the net work. The net work is the net force x component times delta x plus the net force y component times delta y. That was like the old formula we used for that flying bird problem on Monday. Okay, I see that sitting in the parentheses there. So let's make that substitution, right? It's 1 over m times the net work done on this box. That means the sum of the works done by all of the forces. Okay, we're almost there. I know this is the most scintillating derivation, but we're going to get to something very simple in a second. Now I've got an equation that relates the net work done on this object to its initial and final velocities, and all I'm going to do is solve for the net work. Do a little algebra there. I'm dividing by 2 and multiplying by m to get the net work sort of sitting by itself and solving for the net work. So we get the net work is 1/2 times the mass of the object times its final speed squared minus the same thing with its initial speed squared. If you've taken a physics course before, in all likelihood, you saw a definition that you read about in the chapter called kinetic energy. Kinetic energy is defined to be, so if an object of mass m is moving with speed v, we don't really care which direction it's going, all we care about is its speed, then its kinetic energy by definition is 1/2 mv squared. So another way to write this is the net work done on this object between initial and final is equal to the change in its kinetic energy, the final kinetic energy minus the initial kinetic energy. And that is a kind of theorem that's called, sometimes people call it the work energy theorem. I like to call it the work kinetic energy theorem because we'll talk about other kinds of energies later on, but kinetic energy just kind of means energy of motion. The formula is 1/2 mv squared, and that means the faster something is going, the more kinetic energy it has. when something slows down between initial and final, or maybe the simplest case is when it speeds up between initial and final, it's gaining kinetic energy. The change in kinetic energy is positive. Whereas when it slows down between initial and final, the change in kinetic energy is negative. And what this is telling us is that there has to be net work that's negative done if the kinetic energy is getting less as time goes on, if the final kinetic energy is less than the initial kinetic energy. Okay, but notice it's talking about the network. You got to concern yourself with all the forces. And we're going to find that this is useful because it allows us to, if I can calculate easily what the network is, it allows us to figure out what the final speed is if I only know what the initial speed of the object is. So it, just like the kinematics equation, it allows us to jump from the initial to the final without worrying too much about what goes on in the middle. Okay, so this is just a recap of that. Now, I should emphasize here, it's only true if the system is moving as a particle. We didn't allow it to rotate. We didn't allow it to have springy internal forces like a rubber ball that's compressing or something like that. It's got to be just a chunk of mass that doesn't change its shape and it doesn't rotate at all. Your screen sharing is paused. How did I do that? I've never done that before, but let's try doing that again. Somehow my magic thing here is, okay. The same now, so we derived it assuming the forces were constant, but if you run through this argument about the net force being the net work done by all forces being the area under this particular curve, and imagine breaking it up into lots of little steps where the forces are approximately constant, you can actually show, and I'm not going to try to convince you of it here other than the final thing, that even if your forces aren't constant, if you are able to calculate the net work, it will tell you about the change in kinetic energy. And so if you know the initial speed, you can calculate the final speed. That's really how we're going to think of it, right? If I know what it's doing earlier, I want to find out what its speed is later. That's what this tells us. If I can calculate the net work, I could solve for the final speed. Okay, let's do a couple of voting questions and then we're going to work on the worksheet things here just to get the idea of the work kinetic energy theorem. Two marbles, one twice as heavy as the other, are dropped to the ground from the roof of a building. Just before hitting the ground, the heavier marble has how much kinetic energy compared to the lighter one right before they strike the ground? Kinetic energy formula is 1/2 mv squared. This is supposed to be sort of a warm-up one, just to force you to think about that formula for kinetic energy, 1/2 mv squared. So let's see a quick vote. If you're still thinking, that's okay. I just want to see if there's any consensus. A lot of B's I'm seeing, mostly B's, twice as much kinetic energy as lighter one. I agree. Anybody want to make that argument? Put it into words? Why not 4 times as much?
Wouldn't it be because like the mass is twice as heavy, and since you need mass to get force, that would be the like deciding component?
Yeah, it would be the deciding thing. In other words, the formula for kinetic energy, which I believe I'm following Giancoli and using Ke for kinetic energy. The formula for it is 1/2 mv squared. So we got to compare these for the two things. Now, one mass is twice as big as the other. Right before they hit the ground, how do their speeds compare? That's the other important ingredient. They are the same, right? Because they're extinct. We drop them for rest. Yeah, that's the old Galileo Leaning Tower of Pisa kind of experiment. They have the same acceleration. We drop them at the same time from rest. They're gonna have the same speed when they hit the ground. If we can ignore air resistance. It's from the roof of a building and they're marbles. There's probably not that much air resistance. So these are gonna be the same. One has twice as much M as the other one, so it has twice as much kinetic energy. There's nothing profound about that voting question. It's just forcing you to think about that formula. Okay, let's go to the next one. Spaceship is initially moving at 400 meters per second. It's sort of deep in space, far from sources of gravity, toward Alpha Centauri. Right, so it's heading towards this other galaxy. Then it fires its engines constantly to sort of get moving away from Alpha Centauri. So it's going at 400 meters per second towards Alpha Centauri. Maybe its thrusters are aimed backwards. Fires those thrusters. And then it ends up at what we're going to call the final state, 400 meters per second, going the other direction. That takes 2 minutes. What can we say about, there's only one force that's acting on the spaceship here, and it's the thrust force, right? The thrusters are pushing on the ship. What can you say about the work done by the thrust force during this 2-minute period, from when it was heading toward at 400 meters per second to heading away at 400 meters per second? Positive, negative, or zero net work done during that period? All right, some people are holding them up. 2/3 of you are holding them up. So let me just survey the room, get a, I'm seeing A's, B's, and C's, and there's no clear winner here. So let's have a little discussion. Anybody feel very strongly about their answer, or at least want to clarify?
I don't feel strongly, but I was gonna ask, what, don't you have to know how long the spaceship is going forward?
Well, you know, it could have been going towards Alpha Centauri for years before that, but we're just saying right at the moment the thrusters start firing, that's going to be our initial. And then, you know, it ends up going in the other direction. That's going to be our final when it gets to 400 meters per second in the other direction. I don't really care what happened before that. You know, maybe it just, something blasted it really fast right before that, or maybe it had been traveling at a constant speed of 400 for a year before that, but that doesn't affect what happens between initial and final.
The initial is like, during the time period, it's like the 2 minutes.
Yes. So from when the thrusters start firing to when they end firing 2 minutes later. Arthur?
I said 0, because velocities don't change, masses don't change, so it's still.
Yeah, so I think you're thinking of the work kinetic energy theorem, right? Which says that the net work done by, that means by all forces, when we say net, is equal to, and I should unshare this screen so we can see it in the video. That's equal to the final kinetic energy minus the initial kinetic energy. And those are defined as 1/2 mv squared. These v's are just speeds. We don't care about which direction, we just square the speed. Now, what Arthur's saying is that it had the same final speed as the same as the initial speed there. And the mass didn't change, and the 1/2 didn't change. So this is exactly as big as this, and they cancel and give 0 in this case. Even though it turned around, that doesn't mean that there was some net work, right? Even though the force was always pushing on it in the same direction, that doesn't mean that there was that there was some net work in some direction. In this case, it ended up at the same final speed as the initial speed. I think there's a follow-on question. I was about to make another comment, but maybe after ask. So 0 net work was done. That's the answer to that. Here I've just changed the question slightly. Maybe you guys can help me think about this. What about the first half of this period? That's the part where the thrusters are blasting and it's come to rest exactly after 1 minute. And then it's going to start going in that direction, but that's going to be our final. We're not going to think about speeding up in the other direction away from Alpha Centauri. Positive, negative, or zero net work? Somebody, we don't have to vote on this one, but maybe someone can, besides Arthur, can clarify that. Yeah.
Going against it while it's going towards the whatever, isn't it negative power?
That's right. In the first half of it, it's moving in this direction, but the thrusters are trying to push it in that direction. That's the hallmark of negative work being done. And here we're talking about the net work, but that's the only force that's acting on the ship during this time. So that is the net work. So negative work is being done in the first half of the period as it slows down. And then the thrusters keep pushing in the same direction and it starts doing positive work on the ship. And apparently those two cancel out over the full 2 minutes. That gives us zero net work as it speeds that back up to the same final speed. Questions about that? I've lost contact again. Let me click on this. Okay, I think there's one more voting question. Here's a car starting from rest and accelerating to 30 miles per hour. Don't ask me why I chose non-SI units here, but whatever. And then later on, it gets on a highway and accelerates from 30 to 60 miles per hour. Which takes more work, the 0 to 30 or the 30 to 60, or they're the same? This clock in this room has just totally lost it. I mean, it's been going super fast for a week now. Okay, let's see a vote, and then I'm actually going to do a simplified one that's in SI units, and we'll see it's easier to do in your head, okay? I'm seeing A's, B's, and C's. There's not a clear winner here. The answer is B. A lot of people think they're the same in this. I mean, it seems like, hey, 0 to 30, 30 to 60, you're changing by 30 each time. So shouldn't it be the same? That's maybe the surprising thing about this. So let's do, change units a little bit. Here's what I'm going to think about. The net work is the change in kinetic energy. That's the work kinetic energy theorem. Let's think about that. Which takes more work, going from V initial so suppose we go from 0 to 1 meter per second, or 1 meter per second to 2 meters. It's sort of the same thing, except we're just getting rid of the 30s and the 60s. And let's let the mass of the object be 2 kilograms. Why 2 kilograms? Because I got a 1/2 out in front of the m, so that'll cancel it, right? Then the 1/2 m is just 1 in SI units. So as I go from 0 to 1, the net work is 1 joule, right? That's 1/2 times 2 times 1 squared minus 1/2 times 2 times 0 squared. That's 1 joule. As I go from 1 to 2, that's 1/2 times 2 times 2 squared, or 4, minus 1/2 times m times 1 squared, which is 1. 4 minus 1 is 3. So it takes 3 times as much work to get from 30 to 60 as it does from 0 to 30. And you may have noticed this in your car. I mean, that's one reason cars became more and more sluggishly the faster they go. There are other reasons too, because of friction and stuff like that. But if you have an engine that can give out a certain amount of power, it can change your speed a lot when you're at rest. You can speed up really quickly, but all of a sudden, when you start getting towards 60 miles an hour, it takes a lot of effort on the part of the engine to get from 50 to 60. And it's not just because there's more friction or air resistance. It has to do with you're really changing the kinetic energy of your car by a lot more. And that means the engine has to do a lot more work in this technical physics sense of work. Kind of counterintuitive to most people there. Any questions about that before we do worksheet problem? In fact, I think we're going to do a couple worksheet problems. This is the one with that bird on the crazy path on the front, and we're on the back side of that worksheet. If anybody needs one, just let me know. And I think we're ready to do everything on the backside. So let's take a little break. You can talk to your neighbors and work on these. And maybe after 7 or so minutes, we can talk about 3 anyway. I've got other extras if anybody needs them. So the situation is someone's dropping a ½ kilogram ball from a skyscraper from rest. That's our initial. And then our final is after the ball has fallen down by 400 meters. So it's a pretty tall skyscraper. And we're told that at that point it has a speed of 20 meters per second. And it's very close to the terminal speed. In other words, if you keep waiting, it's not going to go much faster because there's a lot of air resistance by the time. So it's not, clearly it's not in free fall this whole time, right? We can't just use A equals 9.8 because if it's close to terminal speed, that means air resistance is not negligible. What net work is done on the ball during those 400 meters? What work is done by gravity during those 400 meters, initial to final? And what work is done by air drag or air resistance? When I say drag there, I mean air resistance or air drag. That's a force acting on the ball opposite the direction of its motion, which is down. Put some answers up on the board so you can check. A is 100 joules. Okay, somebody help me say how I calculated this 100 joules. The net work done by all forces acting on the ball. It seems pretty clear that the two forces that are acting are gravity is pulling it down and air resistance or air drag is pushing back on it. So since it's falling, it's pushing in the upward direction on it. How did I get this 100 joules for the net work done on it? Yeah. Yeah, this tells me directly the net work. So W net is equal to 1/2, and it was a 1/2 kilogram mass. V final was 20 meters per second, right? And then V initial was 0, so that's going to make that one 0. And this is 400 times 1/2 is 200 times 1/2 is 100. SI unit is joules. Just got to get used to that, right? I'm suppressing the units because we're using all SI there. Okay. Then how am I going to calculate the work done just by the gravitational force? Yes. Right. So I think you're thinking of the work done by gravity only on the ball is equal to, you're kind of using that Fx times delta x formula, right? Where as the ball is falling down from initial to final, we'll call that the x direction, right? The direction that it's being displaced. Delta x is it 400? And Fx, the gravitational force x component, well, it's all along the x direction. It's positive. And the gravitational force is the weight of the ball. So that's going to be 0.5 kilograms times 9.8. That's Fx, it's positive, times delta x, which is 400. So it's a little bit less than, this is close to 10 times 400 is 4,000 times 1/2 is 2,000, a little bit less than 2,000. Makes sense. Okay, I don't know much about air drag or air resistance. How then am I going to calculate the air work done by the air resistance force, Sarah?
Dr. Kelly,
Yes.
why do we multiply the work by gravity equation by 0.5?
This is the mass. And this is little g. So this is the weight force.
Oh, okay.
And the weight force is, we're doing the work done by gravity. So what we want is the x component force of gravity here. And that, gravitational force on an object is its weight force. So we're just using good old mg. Okay, I think what Sarah was saying is the net force, the net work is the work done by gravity, which we were able to calculate, plus the work done by air drag on the ball as it moved those 400 meters. And we already calculated this, and we calculated this in B. So we can do a little subtraction and get the one that would be very hard to calculate by itself, right? If you didn't know any other information and somebody asked you, how much work is done by drag? Well, it's a complicated force. First of all, it's not constant. When the thing is moved from rest, there's hardly any air drag force. And then when it starts going fast, the air drag force gets huge. So it's not a constant force. I can't use Fx delta x. So the only way I can really get at it is by sort of backing it out by knowing the net work, which I got from the change in kinetic energy. All right, good. Any more questions on 3? Yeah.
On part B, would we have to just use that equation? I used the first one. We got the same answer.
You mean you use the work kinetic energy theorem?
Yeah, I used that. We got the same answer.
Well, how did you do that? I'm not really sure because it seems like V initial and V final would be the same and the mass is the same. So wouldn't it come out the same?
So like 9.8 as the. I used 9.8 like the M on the first part.
You used M is 9.8. I mean, I believe you that you got the same number, but I don't understand how using a mass of 9.8 would make any sense. In that, 9.8 is usually, and it has units of acceleration, right? The free fall acceleration, or it's the constant g that we multiply a mass by to get the weight. But neither of those would suggest putting it in that first formula. In any case, this formula is, we can think more about it offline and see if there's some crazy way in which you're kind of right. But this is telling us about the net work, which is the sum of the works done by all forces. And here we just want the work done by one force. There's also a drag force that we don't care about in B. And so why we would go to that equation at the top, I'm not sure. But we can think about it more after the fact to see how you got the same number. That's interesting. Okay. I wanted to talk about the last two problems. In fact, we've just got a couple of minutes, so it's perfect for that. Maybe you didn't have time to think about this, but astronaut twirls a 1.5 kilogram ball in a 0.7 meter radius circle at a speed of 3 meters per second. So this is deep space, no gravity, right? But they're doing the same thing I did before, just swinging in a circle at constant speed. How much work does the string do on the ball during 1/2 a revolution? So going from here over to here, 1/2 a revolution later, where they're holding it here, and that's the string. How much work does the string force, which is certainly, it seems to be the only force on the ball as it's twirling around, how much work does it do in between here and here? 1/2 revolution. Anybody have an idea how to do it without really any calculation? Ooh. Yeah, well, so that's one way to think about it. And the answer is definitely that it's 0 work. One way to think about it is anytime you're moving in one direction and the force we're talking about is in the perpendicular direction, you're going to do 0 work. So here we're talking about something moving in a circle, and at every point on the circle, as it's going around in a circle, as it moves through a little displacement from there to there, the string tension force is perpendicular to the displacement. So it does a little bit of 0 work. And nothing changes as you go around. So 0 work from there to there, 0 work from the 0 to, and you go halfway around, you go 3/4 of the way around, it would be 0 work. So it doesn't have to do with the fact that the tensions are in the opposite direction. The answer would be the same even if I did 1/4 of a revolution or 3/4 of a revolution, because it's doing little bits of 0 work as you go around. That's thinking about 0 work is when the displacement is perpendicular to the force we're concerning with. What's another way to see 0 that's maybe a little bit simpler than that way? Yeah. Yeah, we can use the work kinetic energy theorem and say, look, same mass, same speed, it's going around at constant speed, so its kinetic energy isn't changing. So if I take initial to be here, final to be over there, the kinetic energy is exactly the same, and so the difference is 0, and that means the net work done on it is 0. And the net work is the work done by the tension force because there aren't any other forces acting on the ball. So in this case, the tension work is the net work, and it's 0. So that's a different way to think about it. More questions on that one? It's 4 o'clock right now, according to my computer clock. So